Okay, we are ready to start the afternoon session, and the first part will be given by the second speaker of the week. Second speaker was Mariaelena, or Elena for short, Boglione, professor at the University of Torino. And I'm particularly happy to have Elena here to speak about the 3D structure of the proton, and as you will hear from her, transverse momentum distributions. Also because when I was your age, I was doing the first steps into the physics of TMDs, and Elena was a postdoc in Amsterdam, so she was like the senior person while I was young researcher as you are. So it's nice that she's here to present these topics. Thank you, Elena. Okay, and I leave the floor to her, and please, as usual, if you have questions, don't hesitate to ask.
It's a privilege to me to be here today, and I'm really happy to meet all of you. I hope you will have plenty of questions. Of course, as usual, there are no stupid questions. There are only stupid answers, especially my answers. So feel free to say what you think and to make your comments anytime, okay? Don't expect me to be able to go at the same pace that Stefano Forte went this morning. So my lectures will be much slower. And also I will try to be more specific on the conceptual part rather than on the calculations. So I know some of you will not be happy about that. You can stop me anytime, and if you want to go into any detail, provided I know them, we can make any detour around what I plan to do, and according to what my plan is for these lectures. So these lectures are for you, and please let's try to interact as much as we can to make sure that the lectures are useful for you and not to me, right? So this is the program I have in mind. Slight variations can occur on the go, and as I said, we can make any changes any change you would like. Let me just outline this. Today, we're going to go through an introduction and to try to understand what a TMD, a transverse momentum dependent parton distribution functions or density functions is, and how these objects are defined. And then we will also see the zoology, so the collection of these functions which are relevant for transverse momentum studies. This is only going to be an introduction, so it's the way we get started, we get geared up. The main goal of my lectures are to focus on factorization. And as I said, we're going to do this in a slightly more conceptual way with respect to the approach you will follow with Stefano Forte. So hopefully the two lectures will really complement each other. And I have to thank Stefano because this morning he did quite a lot of work, and I will rely on whatever you learned from him this morning for what I'm going to say. We will talk about QCD factorization, and QCD factorizations comes into two different forms. It comes into the collinear factorization theorem, which is what you study specifically with Stefano Forte. And it comes in a different shape, which is the TMD factorization theorem, which is the same kind of factorization applied to transverse momentum dependent observables, okay? Now factorization, why do we insist about factorization so much? Factorization is fundamental because it's the tool by which we can actually apply the theory which is QCD, to predict observables, okay, to compute things. QCD has got a Lagrangian, which is easy to write down, but it's extremely difficult to solve. We don't know how to solve the QCD Lagrangian. The only way we can solve it is to go to some very specific limits. And we rely on factorization to be able to separate whatever is perturbative, so it can be computed in a perturbative expansion, in which we rely on the fact that the coupling constant is small, and so we can expand in a series around the small coupling, okay? But nature is not only perturbative. It's not, unfortunately, is not only about couplings being small. The strong interactions are characterized by a regime which is deeply non-perturbative, where the coupling becomes large, even very large. And in that regime is where hadronic physics comes about. And this is where hadronization comes about. It's where, from the elementary degrees of freedom of QCD, which are quarks and gluons, you form hadrons, which, as the experimentalist researcher among you, can actually measure and see things, right? We don't see quarks and gluons. They are just purely formal objects with which we formalize our theories, okay? So again, factorization, I will tell you this many, many times, but I'm sure that once you go home, you will remember this. So factorization is about separating, okay, what is perturbative, calculable, and what is non-perturbative. So you cannot calculate it, but as we will see together, non-perturbative parts have another important feature, which is the fact that they are universal. Basically, the non-perturbative properties of QCD are a feature of the hadron itself and do not depend on the process in which the hadron is observed. So in other words, if I do Drellian scattering or semi-inclusive DIS scattering, I do observe some properties which are intrinsic of the particle, and they do not depend on the process. So basically, when I measure Drellian, when I measure TMDs in Drellian or TMDs or PDFs in CDIS, in semi-inclusive DIS, I do see the same thing, okay? And if I can, for example, measure a quantity in one process and extract the non-perturbative part by fitting, for example, by modeling from one process, then I can use exactly the same object in another process because of universality, okay? So universality is granted, is ensured by factorization. So part of our work, and you know, the path that I want to walk with you is about studying factorization, seeing when factorization works, but also exploring where factorization breaks. This is potentially even more interesting, right? So we will see when it works, and we will also explore a little bit what happens when it doesn't work, right? So you will become expert, of course. The boundary is extremely fuzzy, and it's very, very difficult to pin down, right? So there is no criteria, there is no way you can tell when exactly you stop being perturbative and you start being non-perturbative? This is a very interesting question, and it's one of the focal point of all the work we do in phenomenology. Alessandro is a great expert in this, right? So there is a very loose boundary between the two regimes, but nature is continuous. You have certainly studied this in your quantum mechanics courses, right? So when you think about a system in quantum mechanics, a system is described by a wave function, and a wave function is a continuous object, right? So any observable in nature is continuous. And so what we do, to answer your question right now, is to compute everything we can perturbatively. Then we try to fiddle with our fits and models and all this complicated machinery that we do to extract the non-perturbative parts. And then we try to put them together. And because nature is what it is, they have to match. So there is a matching region in which we don't really know how to work, because we have techniques which work very well in deep inside the perturbative region. We have ways of getting through in the non-perturbative region, but in between, that's very complicated because both approaches break down. But we know that the two have to match, okay? So this is called the matching region or the central region, where factorization theorems do not apply. Neither the collinear nor the TMD factorization applies, but there should be a matching. And by the way, this gives me the chance to tell you that I will be with you for 4 or 5 hours, but at the beginning of the week. Then there will be Andrea Signori, who comes from Turin for you, and he will do some exercise lectures with you. And the exercise lectures, one of the exercise lectures will be about matching. He's a great expert in this, and he will provide you with some codes in Python. You will be able to use it in Colab, so you don't have to install anything, and you will do a little bit of work on that. He will also do some more sort of blackboard exercise class on the saddle point approximation, and he will do some other classes always on Python about the TMD dependence, the transverse momentum dependence of the PDFs with some toy model, okay? Right, so yes, so the central focus of the lectures will, what am I doing? Will be factorization. A byproduct, I will not be able to use. So a byproduct of factorization is evolution equations. Evolution equations tell us how PDFs or TMDs depend on the hard scale Q, which is the large momentum, which fixes the large scale of the process, okay? So we do a little bit about this. Matching low and large BT, these I will only go through very, very quickly because Andrea Signori, Dr. Signori will tell you about this in more detail. And then if we have time, depending on the pace we go to, we go through some phenomenological applications, okay? So 1, 2, 3, 4, 5 in our initial plan would correspond to the hours. So first hour, second hour, and so on. Now, while preparing the slides and the program of the lectures, I realize we will probably not be able to do this. I will go much slower, but it doesn't matter. We can stop anywhere along the way. As Stefano said this morning, it doesn't really matter how far we go and how many things we do, provided we try to do them well, okay? And I hope you will all be reasonably satisfied with and happy with this lecture. So let's start with the introduction. So as I said, we have a Lagrangian for QCD, which is this specific Lagrangian, and QCD is a gauge theory. So we have not only a quark field embedded in our Lagrangian, but also a gluon field, which is a field which which is a gauge field, so it's gauge invariant, right? This Lagrangian describes the features of the theory in terms of quarks and gluons, which are the elementary degrees of freedom of the theory. But we want to explore and understand how hadrons are built. So what is it that we observe in experiments in terms of the elementary degrees of freedom? Now, while I was preparing these slides, I did an interesting exercise. I went on ChatGPT and I asked to provide some artistic pictures of stuff. So when I said, can you provide an artistic picture of a TMD, this was what came out, right? So you will see some pictures around. And usually when I steal pictures from my colleagues, I put a credit. When you don't see the credit, it means that most of the time it's produced by ChatGPT. Okay, this is not produced by ChatGPT. So we want to understand what are the global properties of hadrons in terms of elementary degrees of freedom, quarks and gluons. And the question is, can we understand the mass, the spin, the size of the hadrons in terms of quarks and gluons? Can we understand the hadronization mechanism? This is a big, big question. This is the most important and the most complicated question to answer, right? Can we understand the hadronization mechanism? Can we understand why we do not observe quarks and gluons in nature, but the only thing that we see are hadrons? Basically is, can we understand confinement in terms of quarks and gluons? And together with these is, can we understand the structure of hadrons in terms of these elementary degrees of freedom with their spin, their mass, their elementary interactions and dynamics? So the way we use QCD is the way you all know. We can deal with a perturbative approach in which we basically rely on the fact that the coupling is small, and then we make a perturbative expansion. We make a series expansion in terms of powers of the coupling constant. We're stuck. Okay. Of course, there are many experiments which tell us exactly, which measure the dependence of the coupling constant with the hard scale of the process Q. And as you can see, the larger is Q, the smaller is the coupling constant. And this is somehow why we try to build huge, enormous experiments reaching very, very large energies, like LHC, for example. This is because the larger the energy, the smaller the coupling. And so the better our perturbation theory works, right? So the expansion, the series expansion will work really well when alpha S is small. But as you go down in energy, alpha becomes larger and larger. And this is, unfortunately, this is where you have to abandon perturbative QCD. But this is also the most interesting part, to me at least, that you can study, because this is when quarks and gluon hadronize. And they sort of make matter as we see it, right? As we can observe it. Okay, so that's the idea. Somehow we have learned that high energy means convergence of the perturbative QCD series, low energy hadronic scales means deep into the non-perturbative region where perturbation theory cannot be applied, and you need some alternative methodologies. Now, there are two main features. One is the hadron structure, and this is embedded into the PDFs, the parton distribution functions, or the TMD PDFs, okay? So these objects tell us about the internal structure of hadrons, of the protons, for example, right? The other important feature is the formation of hadron through hadronization. This is a more dynamical way of exploring exploring this field, of exploring the hadron structure, because it's not just about the hadron structure itself. It's about the mechanism to form hadrons, right? And for these in particular, we rely on fragmentation functions, right? Fragmentation functions are the partners of PDFs, but they describe the formation of hadrons rather than how you can break a hadron into different pieces, into quarks and gluons, and what is the probability associated to a specific quark, for example, or a specific gluon with a specific fraction of momentum inside a hadron. Here is a little animation of the fragmentation mechanism, of the hadronization mechanisms, in which you see at the beginning a quark-anti-quark pair is formed, and then quark and anti-quark move apart from each other until they reach some distance scales in which quark and gluons cannot live alone anymore. So they basically fish out of the sea other quark-anti-quark pairs, and they hadronize. So they do group together. They form groups, which are hadrons, right? Okay. So this is the landscape. There is a proliferation of different functions. They all start with the Wigner distribution function, which is the mother of all functions. The Wigner distribution function knows about the distribution, the density of partons in momentum space as well as in coordinate space, okay? Now, if you integrate the Wigner function on the coordinate space, this is the impact parameter, if you want, of the process, you get TMDs. If you integrate TMDs on the transverse momentum, over the transverse momentum, so you basically sum over all the transverse momenta, you get the PDFs, right? So this is the mother of all functions. If you go along this path, you make your function more and more inclusive. So you observe less details. You integrate over many of the details, and you go to TMDs and then to PDF. And on the other side, you can integrate the Wigner function on the transverse momenta, and you get the GPDs. GPDs only know about the transverse position of quarks and gluons inside the hadron, and if you integrate these over the whole momentum, you get the form factors. Now we we often say we do 3D images. We do 3D tomography of hadrons to learn how they are made. And what we want to learn is how you can go. There are some things which, okay. What we want to understand is how do we go from observables like cross-sections that we can measure, that our experimentalist colleagues can measure, to maps of the structure, of the internal structure of hadron. And this is what these lectures are about. It's what TMD physics is about. Now, this picture I stole from Alessandro Bacchetta, and it in a way it represents what we mean when we say maps of hadron structure. We want to build them some maps of the hadronic structure in momentum space. So we usually we use a probe, which is most of the time is this photon, right? Like in DIS. So the photon is the probe, and we look inside the hadron momentum, the hadron, along one direction, which is the longitudinal direction, the plus direction, if you want, in light coordinates. And we want to have information also on the transverse dimension, right? So compared to collinear physics that Stefano was talking this morning about, collinear is a picture which is very flat, okay? There is no deepness into the collinear picture. The collinear picture is a picture in which basically you only have one direction, which is the direction in which you boost your hadron, the proton in DIS. Okay, you boost the proton very fast in one direction, and you assume that all the constituents inside the proton are traveling in the same direction of the proton itself. Okay, that's collinear, the collinear picture. When you go to 3D, you sort of open up this picture to give deepness, to give more dimensions, okay, to the map that you are building of your hadrons, and you study also what happens in transverse directions, okay? So for example, with TMDs, you can have access to angular momentum of the elementary degrees of freedom of the theory. Okay, here are just some examples of what the final product of this research are in terms of collinear PDFs and of TMDs, okay? TMDs not only depend on the momentum fraction of partons, but also on the transverse momentum, on the intrinsic transverse momentum of the partons inside the proton. And this dependence is peculiar, and it's a specific feature of TMDs. Right. Yes, they are. Well, no, this is only U, okay, here. This is the unpolarized TMD for U quarks. And the different lines correspond to different values of X at a fixed value of Q. In particular, this is a rather small value of Q. When we will talk about evolution, we will see that what happens when you evolve to larger Qs is that typically the TMDs become broader and flatter. Okay, so the larger Q becomes, as Q becomes larger, you will see, I'm messing up with this, you will see this peak going down, 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 and the distribution becoming larger and wider and wider. Okay, so the shape sort of dilutes in the Q direction, right, as Q grows. I'll try to show you some animation of this later on. Now, ChatGPT again. I told him, can you make a picture of a fragmentation, of a TMD fragmentation function? And this, I think this is actually quite nice. It doesn't have any scientific deepness, but it looks nice. What we actually imagine for the fragmentation functions is something like this. This could well be an E plus E minus annihilation process in which you scatter E plus E minus like they do at Bell, for example, or at Babar, or in the old LEP. You scatter two leptons and anti-leptons, E plus E minus, for example. You produce a photon or a W or a Z. The photon or the W or the Z produce in turn a QQ bar pair, and the QQ bar start going apart from each other. And at the beginning, the scale distances are very, very small, and the energy scales are very, very large. So we are in the asymptotic freedom regime, right? In the perturbative part, where we can use the perturbative expansion. But as the two quarks separate each other, they sort of go further and further from each other. At a certain stage, then confinement starts to work. It means you're going to lower energies, you go to larger distances, and also you go to larger time scales. So at that stage, the time is wide enough, is large enough for the two quarks to be able to negotiate through strong interactions, okay? And this is when hadronization starts. So when the time and distance scales are large enough, then strong interactions comes about, and you get into the non-perturbative regime where hadronization happens. So in other words, quarks and gluon cannot live separate from each other anymore. So they start negotiating interactions with other quarks and other gluons, and they come together to form hadrons. And only at that stage do we observe them. We're able to observe them, okay? Is this clear to everybody of you? Right, this is something you already knew. Am I right? Okay, so there are many different fragmentation functions. The fragmentation function we are most familiar with is the single hadron collinear fragmentation function. This is something you see in specific processes like semi-inclusive deep inelastic scattering or E plus E minus annihilation into hadrons, okay? Then there are the TMDs. TMDs are very similar objects, but they also depend on the final transverse momentum, which is measured of the hadron, okay? This is the final momentum of the hadron, and it's unobservable. It's something that can be measured. Then there are dihadron fragmentation function, which Alessandro is an expert on, and they basically are related to the probability to the process hadronizing into a pair of hadrons. And then there are inclusive jets, which we're not going to treat in these lectures. So jet physics is when you observe these very energetic sprouts of hadrons without measuring the features of one particular single hadron in your process. And other kinds of very acrobatic forms of fragmentation functions. Now, until now, I just use words, but we have to give a definition. And the only serious definition you can give of these objects, as Stefano taught you this morning, is to give an operator definition of this quantity. So basically, we refer to a process like this, in which you have a lepton and a hadron process. You have a process initiated by a lepton scattering against the hadron, and then you produce anything, okay? And you don't worry about what you produce in the final state. This is basically DIS. And this is the operator definition of the correlation function, the quark-quark correlation function, from which all the PDF stem. So it is basically the Fourier transform of an expectation value of these funny products of wave function. And I don't know if you remember this morning, Stefano was talking about exactly these objects here, okay? So the hadron has momentum P, and we take this expectation value on the states of momentum P, okay? And these are the field operators. So field operators are the fields of the theory. So they are the fields of QCD, and they represent quarks and gluons, quarks in this specific case, okay? So these are fields which represent quarks. And you put in a quark in a space time point, which is this psi here, and you take it out in the position 0, okay? So I'm sure you all did a course of quantum field theory, and what is this structure? This is the structure of the propagator in quantum field theory, right? In quantum field theory, the way you test the states of a system is you take a system in a specific state, which usually is the fundamental state of your theory, okay? And then you put in a particle. It's a test particle. So you put in a test particle in a specific point of the space at a specific time, okay? You leave it there for a little while, and then you take it out. So these fields here, psi and psi bar, are exactly that, right? So you put a particle in a point, and you take it, you leave it to evolve for a little time and space, and then you take it out. And you ask, what is the probability of the state of the system to be exactly the same, to have remained exactly the same? Do you know what I mean? Do you understand what I'm saying? Do you want me to write it on the blackboard? Right? It's clear to everybody, okay? So that's the same thing. So in a way, these correlation functions are related to the propagators, and so they know, they contain information about the dynamics of the theory, of the quantum field theory of quarks and gluons, which is QCD. But any of you who've been careful would ask, what is U? What is the role of U? Does any one of you know what is U and why it is there? Right. It's exactly that. This is called sometimes a gauge link. So this object here, without the U, without this operator here, is not gauge invariant. This is a specific feature of gauge theory. If you take any theory like p to the 5 to the 4th, for example, you don't need any gauge link. But if you work in a gauge theory where the matter fields couple to the gauge field, then you need that because to restore gauge invariant, okay? So this quantity here without this U link, this U Wilson line, will not be invariant under local transformation, local phase transformation, e to the I alpha of x multiplied by psi, okay? So you have to restore gauge invariant, and you put in this U link here. We will speak about this in more detail in the future, in the next few hours, because the presence of this factor here is one of the points which make factorization complicated, okay? So, so we will come back to this. I think I have a slide. Yeah, we will. So that's the idea. So you have to you put in a particle here, and you take it out in there, right? Remember that in the belly of psi and in the belly of psi bar, there are creation and annihilation operators, right? So this is the way you put in a particle here, and in the belly of this, there is so here there is a creation operator, and here there is the analogous annihilation operator, right? Now the gauge link is a quantity which actually leads you in a gauge invariant way from one point to the other, right? In space-time, along a specific path. Okay. No, you can't. You can't because of the locality of the transformation. So if you want, you know that to build a gauge theory, you need a local symmetry. You have, the theory has to be symmetric. The Lagrangian has to be symmetric, invariant, for local phase transformation, right? So as soon as you put a space-time dependent in the phase of your transformation, once you take the derivative, you get a new term in your theory, which is the derivative of the phase. Let me just, I don't want to teach you a class of quantum field theory, but I think this is important, and it has to be clear. So you start with your metal field, and the Lagrangian is this, right? Can you see? Is it too small? You can see? Yeah. And you observe that if you transform psi in a psi prime, which is e to the I alpha psi, okay, nothing happens. The Lagrangian is invariant for this transformation simply because alpha is a number, okay? And so being a number, you can take e to the I alpha from this side to this side, okay? So of course, psi bar will go in psi bar prime, which is e to the minus alpha psi of x, okay? And when you do your you put in your transformation, this is an internal transformation. It's a transformation which doesn't alter, it doesn't cause any variation in the space-time. So basically, what happens is that these phases can just match to each other, and they give you the identity, okay? So the Lagrangian is invariant, right? However, if you say, what does it happen if alpha depends on X, then this is a hot mess, because when you take the derivative, when you do d mu alpha of X, d mu is the derivative with respect to x mu, okay? And so the derivative of this exponential factor will be e to the I, will generate a different term which contains this term as well, okay? Because the derivative with respect to x mu will act on this factor as well. And your invariance is ruined, okay? And this is the basis of gauge theories. So what do you conclude? That how does the story end? The story ends in this way. So if you make a local transformation, you lose invariance. If you want to restore invariance, you have to do an exercise, an acrobatic exercise. So you have to say, I put in my theory a new field, okay? And this field has to have a very specific feature. It has to be gauge invariant. So the field must be A mu, okay? And A mu, sorry, I'm diverging here, but this is so nice that I always get excited. A mu is exactly what you need, because you can transform it to A prime mu, okay, which is the same as the original A mu, plus the derivative, the four-dimensional derivative of any function of x. So this is a function which is completely arbitrary, okay? This is gauge invariance, right? And so you say, I invent a new theory, which is a gauge theory, in which I have to have at the same time two fields. One is the matter field I started with, and the other one is my gauge field. And when the matter field transforms like this with a local transformation, at the same time, the gauge field, which is there, will transform in a gauge way, with a gauge transformation, in which this function, which is arbitrary, and I can fix it as I please, is exactly alpha, okay? And then I put a minus sign here, and this d mu alpha of x cancels the mu alpha of x that I have here. And in the Lagrangian, the symmetry is restored, okay? So that's about, when they tell you we deal with a gauge theory, it's this concept here. A gauge theory is a gauge which is based on the existence of a matter field which transforms in a local phase transformation associated with a gauge field which can compensate for the transformation of the first field and make your Lagrangian invariant. Of course, what happens is that the two fields at this stage are coupled, okay? And this is the way you build QED, for example, in which the matter particle, the electrons couple to the gauge field. And when an electron moves, we know it generates a field. Yes. Yes. Okay. Bear with me. I just didn't. Yeah. Yeah, I just didn't. Sorry. Yes, you have to put all the alphas and you have to put the couplings as well, right? So the invariant derivative will have the proper I and also the coupling Q. I just didn't bother about writing all of this, but yes. Okay. Okay, so I totally forgot why I started talking about this, but yeah, the gauge link. Okay, so This is a gauge theory, and it's a very complicated, it's not only a gauge theory, it's one of the nastiest gauge theories you can possibly imagine, QCD, because it's non-abelian, okay? So it piles up, strange and silly and difficult to deal with effects do pile up and give you a lot of complicated stuff that you have to deal with, okay? Now, I don't want to dwell too much on these things, but did you ever heard about the Aharonov bomb effect? Okay, so these gauge links, these Wilson lines, are basically the same as the idea of what you can detect in an Aharonov bomb effect, in which you have a piling up of all the phases which are picked up by the particle when it goes through a field. In our case, it's a color field, okay? So if we have time, we can talk about Aharonov bomb effect as well. Once you are happy with your operator definition, and once you know how to make a Fourier transform, you are more or less done. Just, there's something there's something weird here, which Stefano didn't, I think he mentioned it at a certain stage, but I just want to point this out to you. Do mind that these P states are hadronic states, okay? But here, we talk about quark states. So basically, there is a slight mismatch. Nothing to worry about, it works. But there is a slight mismatch between what you would expect in a propagator in quantum field theory, in which you use the interaction picture, where you take quarks fields at infinity, at plus infinity and minus infinity, right? So they are asymptotic states, quark states, right? Whereas here, you build these expectation values taking hadron states, okay? So this, in a way, embeds the features of hadronization. So if you go to far distances, you don't have quarks and gluons anymore. You have hadrons, okay? So this is another complicated features of QCD, which doesn't have an analogy in QED, for example, okay? You cannot have quark states at infinity, at plus or minus infinity, because by the time quarks are sufficiently separated, they don't exist anymore. You only have hadrons, okay? So that's the definition. Is everything okay? Do we stop for a few minutes? Let me just see what, yeah, since we still have 5 minutes before 3:30, I will just go very quickly to the processes, because this is just going through something that you already know. So one of the reference processes that we will use is deep inelastic scattering. And I am not going to go into the details, because Stefano Forte this morning explained you very much in detail about deep inelastic scattering. So here is a little cartoon in which you see the steps in terms of factorization. So let me just give you the description of DIS in terms of factorization approach. So you have a probe, okay? And this probe will scatter with a proton, for example, okay? And the probe is a photon in deep inelastic, in normal deep inelastic scattering. The proton has quarks inside, okay? And the scattering happens with one and only one of the quarks inside the proton. Then the proton will have some remnants. We will travel through space and time, okay, on their way, but the blue and the red little balls, which represent the photon and one of the quarks inside the proton will go away back to back. Okay. And now you have a recoiling electron parton pair and a final state of free partons. Okay, you don't observe any of the hadrons which come out in a deep inelastic scattering. Most often we use light cone variables to study these processes, and just in case you can find a little bit of details about how you use light cone variables. And this is that the kinematics relations that Stefano showed you this morning, right? With all the observable quantities. And of course, the deep inelastic regime is taken in the Bjorken limit when Q squared and P dot Q go to infinity, okay? They go to infinity while keeping XB fixed. Yes. Okay, when you have a polarized target, so imagine you do a polarized proton, for example, then you have to deal with spin, and the way we do it is with the polarization matrix, which you can write in this way, where SI are the spin projections and sigma I are the Pauli matrices. We will not dwell too much on this. I will give you a few examples of spin effects, but we will just go through them conceptually. Okay, so before we start with cross-section, let's take a break for 5 minutes, and then we reconvene. Alessandro, what time do we reconvene? 10 minutes? Okay. If there are any questions, of course, I'm here. Okay. So we want to talk about cross-sections, of course. In QCD, you need to have some infrared safe observables. Infrared safe observables are observables which do not present any divergence. And cross-sections are the observable that we usually use, right? So this is the notation we will use, and you are already familiar with this because Stefano Forte this morning told you about the leptonic tensor and the hadronic tensor and how they are made. And also we will use this kind of diagrams in which you see that you have a square, right? So there's a cut here, and basically they represent these matrix element multiplied by its corresponding complex conjugate, Hermitian conjugate part, right? Okay, so the cut represent particles that go to the final state and they are on shell. Okay, so there is a selection, as there's a delta function, as Stefano was saying this morning. Okay, so the cross-section will be like this, and the leptonic tensor represents the upper part. The leptonic tensor is easy because you can compute it in QED. And QED is the simplest of the gauge theory that we know, and we can handle with it very cleanly, okay? The complicated part is what comes below, and this represents the hadronic tensor. And as we saw, the hadronic tensor is not completely calculable in perturbative QCD. It's got a part which can actually be expanded and calculated in perturbation theory, in perturbation, as a perturbation theory, but it also has a part which is deeply non-perturbative, okay? Because it contains information about the structure of the hadron, and this is not calculable. We have to rely on experiments or on model or on lattice QCD, whatever. This is something that Stefano was talking about this morning. So the scattering electron fills the electromagnetic field, right? So the electron is charged, and when it goes close in DIS, for example, the electron, when it comes close enough to the proton target, it fills the fact that the proton is charged, and they do interact through an electromagnetic current, which is J, right? Is the J that Stefano was using. Now it's gone, but it was on the blackboard this morning when he introduces the definition. And here, when you take the complex conjugate, you have to be careful, because in between here, you have a complete set of the intermediate, of the final states. And this is the sum of all the states that you do not observe in this case. So in a more technical way, we say that this is a very inclusive kind of process, okay? DIS is the most inclusive process you can think about. And it's because of this very large degree of inclusivity that it works so well. Factorization is the easiest kind of collinear factorization in DIS is the easiest to prove, thanks to the fact that there is such a large degree of inclusiveness here. Okay, you sum over all the final states, sum over all the final particles. There is this concept about factorization which I would like you to take home as a message. The more you look into the details of the process, the less, in other words, the less inclusive you are, the more complicated factorization becomes to prove, okay? So the more you look inside the details of your hadron, the more specific you become in picking out one final state rather than all the others, the more factorization becomes complicated to prove. And it has to do with the fact that you, instead of summing over all the possible final states, you basically break this completeness of the Hilbert space where you're working on. Okay. You can do a sort of tensorial analysis, and you take all the vectors that you have available in your process, and you combine them in all possible ways, and then you make this kind of analysis. And of course, you have to tensorially you have to have a rank 2 tensor here. So you want to build an object with 2 indices. And you can do it with G mu nu, the metric, or you can combine Q mu and Q nu. You can combine P mu and P nu, or you can mix them up, okay? And these are the only possible ways in which you can create, with the vectors that you have available, the 4 vectors that you have available, you can build a rank 2 tensor. And then each coefficient, A, B, C, and D, that you saw before, will correspond to one particular structure function, right? I don't want to spend too much time on this. I think Stefano talked about structure functions, and he also pointed out that in modern times, we don't really much rely on structure function. We work rather with pattern distribution functions or fragmentation functions. Now, up to now, we've only talked about collinear processes. There was no transverse momentum mentioned yet. If you want to gain some information on the transverse momentum in your process, you have to become less inclusive. You have to become more picky about what you measure. So consider a deep inelastic scattering as before, but instead of summing over all possible final state, now you become more selective when you say, I want to measure one specific final state. For example, a pion, okay? You teach me. I want to pick out a pion, okay? So you have your electron coming, you have your proton coming, they see each other, they exchange a photon. The photon is your probe, which goes inside the proton and interacts with one and only one quark. At that point, the struck quark comes out of the interaction point. These are the remnants going away with whatever is in your process, but the struck quark, when it gains some distance from the process, it cannot live on its own anymore, we said in QCD. So it negotiates its interactions with other quarks and gluons from this hot mess, which is in this little cloud, and it produces a final state, which in particular can be a pion or a kaon or whatever, another proton, eta, or depending on the experiments, you can have as many as you want. Okay, but you pick only one. So this is why this is called semi-inclusive. Okay, so you're not completely inclusive anymore because you're measuring one. And here you can have other final state produced, but they all go together with something which you sum over. So basically you have one more step with respect to what we had before, which is step D, in which you observe the final state. And this is just the kinematics. So in this case, you have a one hadron, which is produced in the final state, and this hadron has a momentum, a 4 momentum, and this momentum is not collinear because we gave up on the collinear approximation, and so it can have a transverse component of the momentum. Transverse component means that if this is the longitudinal direction, the collinear direction, the proton can go anywhere in a cone, right? So having a transverse momentum means that it also has an azimuthal angle, okay? So you open up your space, you are in 3D now, okay? And the transverse momentum can be anywhere in your three-dimensional space. And you no longer have just a polar angle, you also have an azimuthal angle. And this is relevant. I mean, this azimuthal angle is what makes spin physics, if you want, polarized physics interesting in all the experiments that our colleagues are measuring every day. There is something that I didn't write on these slides, but I really want to tell you. It turns out that if you want to study transverse momentum dependence, you also have to deal with spin. This is because you are introducing a new vector, and this new vector, the transverse momentum, turns out to correlate strongly. We are in quantum mechanics, remember, so there's entanglement. And it is this specific transverse momentum vector which couples to the spin of the target, for example, or for fragmentation function of the spin of the final hadron, right? So in a way, when we talk about spin physics, we talk about transverse momentum TMD physics. And when you talk about TMD physics, we cannot forget about spin because there are subtle, very non-trivial correlations between the two, okay? So at the beginning, when I was younger like you, 1,000,000 years ago, we would talk about spin physics, right? Transverse momentum, TMDs, it's a word which came afterwards. But at that time, even, you know, when dinosaurs were grazing around in the fields, and I was young, we already had this very clear feeling that spin and transverse momentum correlations were crucial to and inseparable somehow in this kind of studies. Okay, now The cross-sections in CDs is written in the same way. It's a convolution of a leptonic tensor and a hadronic tensor. The leptonic tensor is always the same, of course, because this part of the interaction doesn't change. It's pure QED, okay? But of course, it's the hadronic tensor which changes, and in particular, the hadronic tensor is now feeling the fact, it knows about the fact that you're producing a hadron in the final state. And the cross-section that you're interested in CDs is a cross-section which is differential not only in the X-Bjorken, which is, if you want, the momentum fraction of the initial, of the parton in the initial proton, in the target proton, but it's differential in the momentum fraction of the final hadron. ZH tells you about how much of the momentum of the quark gets into the final state hadron, right? So it's the same as XB, but it's reversed, right? Then you are differential in phi h, which tells you about the azimuthal direction of the final produced hadrons. Experiments like COMPASS or Hermes, they measure these angles specifically, right? Am I right? And then, of course, you want to be differential in pH, which is the transverse momentum of the hadron, which is observed. It is a quantity that you can measure. Okay, here again about structure functions. Just don't worry about this. Now, I just want to show you this difference. This is if the cross-section is not polarized, so you are not worrying about any of the spins involved into the scattering, and you basically have 1, 2, 3, 4, 5 structure functions, okay? Structure functions are convolutions of PDF and fragmentation function TMDs and FF TMDs. But if you want to do spin physics and you mind about the polarization of the nucleon, of the target, then this degenerates into a huge number of possible different structure functions. And there are our colleagues who actually, through a Fourier analysis of these azimuthal dependencies, they actually study each and every one of these structure functions, okay? Now, we have to talk about TMDs. I want to give you can I just keep on these? We saw already the operator definition for the PDFs. This is for TMDs, and it's basically exactly the same. So you have to do the Fourier transform of these correlation function. In this case, of course, you not only have to worry about the longitudinal momenta, but also you have to worry about the transverse momenta, and you have to conserve globally the momentum. And here is a little picture of the gauge link of the Wilson line, which we are not going to get into any detail, not because I don't want to talk about that, but because we're going to see it in more detail maybe tomorrow. Okay. So if you look at collinear correlators, you don't have transverse momentum, you basically have 3 PDFs. This is the unpolarized PDF. This is the longitudinally polarized PDF. So this time you mind about the spin of the target. Say the target is a proton, right? And a proton can be longitudinally polarized, it means that the spin is aligned along the longitudinal direction. So it's aligned along the direction of motion, or you can have a spin which is transversely it's aligned in the transverse direction, and so you have three of this function. F1 is the unpolarized one, G1 is the longitudinally polarized, and H1 is the transversely polarized PDF. Here you don't have any transverse momentum yet, and then you have this function, which is the tensor polarized PDF, but we're not going to be interested into these. When you go to TMDs, when you introduce the dependence on the transverse momentum, these three functions that you have before unfold into 8 different possible functions. Why does this happen? Because you are adding 2 more transverse directions, right? And so in this case, you can, for example, appreciate the difference between a transversely polarized spin of the hadron and the direction of the spin of the quark inside the hadron, right? So for example, you can have a function which is called the Sivers function, okay? This Sivers function is related to the probability of finding an unpolarized quark into a transversely polarized proton, into a transversely polarized target. And what is interesting is that this function is 0 if in the collinear approximation. So this is a completely, genuinely new object which comes about when you talk about TMDs, right? Other very peculiar functions are these functions here. This is called Wong-Gear, this one and this one. Okay, these are related to the probability of finding a longitudinally polarized quark into a transversely polarized hadron, and this is related to the probability of finding a transversely polarized quark into a longitudinally polarized hadron. Now, let me show you this picture here, which I think this is something that Pete invented many, many years ago, and we all learned from him, so we all took these pictures from here. So the idea, the names of these objects, which can seem a little bit arbitrary and mad, crazy, is in fact not totally crazy. So F stands for unpolarized, and it's referred to the polarization of the quark, of the parton, right? G is longitudinally polarized, and again, it stands for the polarization, longitudinal polarization of the quark. And H is transverse polarization. One means that when you, basically, it means that it's the leading order. It's the most leading object. In other words, when you integrate over the transverse momentum, this survives, okay? So this is the unpolarized function, F1. G1, longitudinally polarized, and H1 is transverse polarization, right? Now, this letter here, T and L, capital, refers to the polarization of the hadron, okay? So, for example, the Sivers function, as I told you, is a unpolarized quark inside a transversely polarized hadron, okay? This is pretty weird because it refers to a transversely polarized quark into an unpolarized hadron. You see, there's no T or L in here, okay? And L is for longitudinally polarization. So basically, what happens is that a new world of different possibility opens up, right? So you can have a hadron which is transversely polarized, and inside the hadron, in the belly of the hadron, there are a bunch of quarks, and they are polarized longitudinally, okay? So this is the G1T, okay? the hadron is transversely polarized, but the quark inside, the parton inside it, is longitudinally polarized. Now, while we know we do know quite a lot about, for example, the unpolarized distribution TMDs. We know rather well the Sieverts function. This function here and this function here are poorly known, as well as this function here is rather poorly known. Okay, so the physics becomes much richer, but also a bit more complicated, and we need very specific studies, analysis, data analysis to actually single out these contributions. Now, for the fragmentation function, we have a similar argument. Also, in this case, we have gauge links which come into the picture, and this is the scheme of the fragmentation functions. Now, again, we have 1, 2, 3, 4, 5, 6, 7, 8 functions. But fortunately, in most of the cases, we study spinless final states. So we only worry about 2 functions. So we don't, the function in which there is no capital L or no capital T, spinless final hadrons in which we only worry about the unpolarized fragmentation function, TMD fragmentation function, and this function here, which is called the Collins function. And the way I mentioned, and the reason why I mention it is because we're going to give some example about the Collins effect in the next few lectures. This here is the density, it's related to the probability that an unpolarized quark hadronizes in, that a transversely polarized quark, H, hadronizes into a spinless hadron, like a pion, okay? So although the quark is polarized, during the hadronization process, okay, during the confinement process, the spin gets averaged over and the final state is unpolarized. Okay, this is a particularly interesting function because this function here, when integrated over the transverse momentum, goes to 0. So this function here doesn't have any correlated PDFs, right? So this function here, if you integrate it over the transverse momentum, gives you the D1 unpolarized PDF. This one also gives you the longitudinally polarized PDF. This part here gives you the transversely polarized PDF. But these functions here, which have a perp index, when they get integrated over the transverse momentum, they go to 0. They don't have any counterpart. They don't have any PDF counterpart, okay? So they are a little bit more complicated to model as well. Okay, if you are willing to work a lot, you can do all of this work also for gluons, and you can define gluon correlators and gluon parton densities as well. This is something that we will not really study in the course of these lectures. Now, here we already come a little bit further into the factorization picture. So how do we write the transverse, the cross-section, or how do we calculate, how do we compute the cross-section of a CDS process, okay? It's factorization which comes in our help. We can actually compute this cross-section if we are able to separate out the hard part, which is deeply perturbative, and we can compute it with Feynman diagrams, okay? And it's, if you want, it relies on the possibility, on the possibility to compute a Feynman diagrams to any order of, oh gosh, sorry. Must be somewhere. Okay, it basically corresponds, sorry, I'm messing up. It corresponds to our ability to compute a Feynman diagram in which we have the initial and the final lepton coming in, the photon and the quark, the ingoing quark and the struck quark going out, okay? This is something that that Stefano mentioned this morning when he was talking about how to connect the operator product expansion to the parton picture and further to QCD, okay? You can do it provided you can separate out these part of the process, of the cross-section, if you want, which is H. H stands for hard. Hard means high energy, small distances, small time scale. So it's the regime where perturbative QCD apply, and you can compute everything in terms of quarks and gluons. So basically, you can compute everything in terms of quark fields and gauge fields, according to what we were saying before. But then this doesn't come on its own, of course, because this only lives at small distances and small timings, okay? When you allow distances to become wider and times to get longer, then you have to worry about hadronization, okay? So about the way, for example, final state interactions among quarks are negotiated to actually produce your final hadron, okay? And the same here. You have an initial proton, okay? But the photon only interacts and scatters with one of the quarks which are inside the proton. So basically, you are in a picture in which you have your PDF here, your fragmentation function here. They embed in your cross-section. Now I have to go the way back where I was. There. So basically, you have the hard part, which is this one, okay? This is Feynman diagram. You can compute it in a series expansion in terms of the couplings where you are sure that your coupling is small. And these are the two PDF, the TMD PDF and the TMD FF, which separately, when distances become larger, so these objects must be very well separated in time and distance and also energy scale. They describe the structure of the initial proton that you use as a target, and separately the fragmentation function, which describes the hadronization process, so the mechanism which leads a quark or a parton or a gluon or whatever you want, an elementary degree of freedom of your quantum field theory to become the final hadron, okay? And this only works if everything is very well separated, okay? Very well separated means separated in terms of large distances, large time scales, okay? And also energy, which become much smaller, okay? So basically, it's where confinement comes into play. Okay. So your structure functions now become convolution of two partonic densities, one for the initial states, and this is the PDF or the TMD PDF, and one for the final states, for the production of the final hadron, which is the fragmentation, the TMD, okay? And of course, you have to have combination which should be chiral even, and they have to respect all the symmetries of the theory. So of course, the dominating term is the convolution of an F1 and a D1, an unpolarized quark with an unpolarized, an unpolarized parton in the initial state, giving rise to a spinless hadron from an unpolarized quark in the final state, okay? But then you can have all sorts of different combination. For example, you can have H1 perp with H1 perp. This means a transversely polarized quark which scatters against the photon, and the struck quark ends up maintains a transverse polarization because this is still an H, and fragments into a pion or a spinless hadron. Okay, these are effects which you can only have when you have transverse momentum. When you work in a transverse momentum dependent picture. This is the so in a way this is a Collins effect, and this is the Sievers effect. Collins effect because this one is the Collins function. Sievers effect because this is the Sievers effect. So in this case, you produce an unpolarized final state with a polarized, transversely polarized quark inside an unpolarized, an unpolarized quark inside a transversely polarized hadron target. Okay. Now, this can become rather cumbersome, and I don't want to bore you with all this zoology and degeneration of possible different terms. I just want you to remember there are plenty of possible different effects, but we are only interested into three of them. One is the unpolarized cross-section, F1D1. One is the Sievers effect, F1T perp times D1. And the other one is the Collins effect, okay? Only that. All the others are very interested, but not relevant in what we're going to say. I forgot to tell you something. What we call convolution, when we talk about convolution, like in this picture here, when we talk about factorization, you always see this symbol here. This stands for convolution. A convolution is an integral over shared momenta in the process, okay? So this is not a product. This is not a simple product. This symbol here means that you take this function and this function, the product of these two functions, and you integrate it over all the momenta which are shared, so which are related by a conservation law, okay? And in the slide that, yes. Absolutely. Yes, exactly. So this morning, Stefano was talking about Mellin transforms. These two things are completely unrelated, okay? So to us, I mean, this is a very general definition of what we mean by convolution, and doesn't apply to, I mean, the Mellin variables are more related to the fraction, the momentum fraction, okay? And not to the momenta, okay? So when we talk about convolutions, we are actually integrating these product of functions over the shared momenta. And you see, I talk about shared momenta because there is a conservation law which relates PT and KT, where KT is the momentum of the final hadron, of the final quark with respect to the hadron, and PT is the momentum of transverse momentum of the initial quark inside the initial hadron. Okay. Higher twist, I leave Stefano to talk about higher twist, but he mentioned this morning that higher twist are powers in the ratio of m/q. Okay, so we talk about how higher twist functions, which are subleading compared to the twist 2 dominating function, when the contribution in the expansion is weighted by powers of m/q. And of course, if you go to higher twist function, to higher twist level, you will find many more TMDs coming into play. And this is this is a very interesting study because, as you see, the expansion is in terms of another quantity. It's not K transverse over Q anymore. It's m/q. And so sometimes, well, most often is very difficult, almost impossible to say whether these effects are actually subleading or not. They can play a role. Okay, so I think we can stop here. I just entertain you for 3 more minutes. I collected a few references here that might be useful to you. The book that I refer most often in the rest of my lectures is the book by John Collins, Foundations of Perturbative QCD, where he explains in great detail about TMD factorization. Okay, then there are other books which are interesting and certainly you know, worth consulting, which I put there. Some of them are old books, traditional books like Muta, and others are more recent. Then there are a collection of lecture notes. This is just a very personal selection. There are many, many more on the market. Papers and reviews. Maybe this is a little bit old, but you know, new and more comprehensive reviews come out every year, every month on the internet, on the archive. There's also this Hugs pedagogical page which can help you. Here you can find any kind of references. Some books, Griffith, for example, I'm just saying because my eye came on these Griffiths and Halson Martin are very simple book. So if you know very little, almost nothing about particle physics, you can rely on this book, which go through the very basic, whereas other are more much more involved, much more detailed, much more written in a very complicated way. I think I don't know whether Alessandro agrees, but one of the most complicated is John's book, right? So you can pick anything that you like, and you basically go through all shades of possible complication and details that you like. Experimental overview, of course, the EIC yellow book and all other possible, you know, again, shades of things. This is mostly for the exercise classes, which will be done by Dr. Signori, who will be with us starting from tomorrow night. Google for the analytic exercise class on Saddle Point. He will do everything on the board, and so you will be able to follow. You don't need any specific abilities. For the computational part, he will provide you with some codes ready-made. I think they are basically Python codes, and you will be able to use Google Colab, okay, to run them. And I think we can stop here for today. Tomorrow we will dig deeper into factorization, okay? So if there are any questions, I'm here. Otherwise, have a very nice evening and night, and see you tomorrow.